Hello, folks. I think we'll just wait a few minutes for our audience to arrive. Currently have 8 people viewing. And maybe we should do a little bit more than 8 people. Although it is being recorded, so... Yep. Okay, oh, we've got chat. Good morning. Yes, good morning indeed. So, I guess that's gonna have to do for today. Oh, 15, there we go. That's the official start number, is 15. I understand it's a Friday. I understand it's the Friday of the last full week of term. But, you know, we should still probably at least pretend like we want to do some school and stuff. So, we're going to get into an idea called polymorphism. We had just finished with this idea of inheritance. We had just defined a class for spells that's kind of similar to the one in Dungeons and Dragons. The operative idea there was that we were defining one actually. We didn't quite do the second one because it's so trivial. But we have healing spells as a type of spell. So healing spell inherits from spell because it's a more specific type of spell. Pardon me. And we see that we can redefine the cast method of this class in order to update itself to the new functionality that we expect from our healing spell class. Most particularly, it takes a target creature and adds to that target creature the number of the number of points that the healing spell is worth. So that's sort of where that is. However, I have, through the course of this example, been sneakily introducing a concept to you guys called polymorphism. So polymorphism is actually a fairly general term within the context of computing. It really starts to come into existence when you start getting object-oriented languages. Polymorphism, or polymorphic design, derives from the ancient Greek polis, meaning many or much, and morphe, meaning shape or form. So it's many-shaped or much-formed. So, generally speaking, we are focusing on the idea of polymorphic functions. We have basically the polymorphism that we are describing in this particular lecture or this topic, this set of slides. It's divided into two camps, two categories. We have overloading, which is something that we actually saw in topic 10 to begin with. That's a type of polymorphism. And we have overriding, which is a type of polymorphism that we saw in the spell example. We're going to get into the difference between overriding and overloading, because there's a technical difference in C++. So, a derived class may provide a new definition for a member function of the class, similarly to how healing spell provides a new definition for the cast function. We say that the new definition overrides the old one. So you have the old definition, the new definition overrides it. So it sort of takes its place. It gets out its sharp elbows and butts in line. The function has different definitions depending on which context it's used in. So, although we are overriding the cast function within the context of the healing spell class, within the context of the spell class, we would still be dealing with the old definition. The base class is still has accessible the base class instance of the function definition. So you can see in our definition for the healing spell class, we are actually using said definition by entering into the base class's namespace using the scope resolution operator. So that's a thing to keep in mind. When a function has been overridden, obviously, if you have an object of the base class, any overriding that's going on inside of any derived class isn't going to apply to the base class. It's only going to apply if you're within the context of the derived class. So there you go. Yeah. So, overriding versus overloading. Upon first examination, overriding seems to have a lot in common with our previously established idea of overloading. Both of them are mechanisms for having one function have several implementations. This is the concept of polymorphism. It has many forms. It has many shapes. One function can be many things. So, in overloading, the correct function definition is selected by examining the number and argument and type of arguments to the function. No two definitions may have the same type signature. So if you recall way back to topic 10, all that time ago, overloading, there we go. If you remember, the thing that we were overloading here was type of, right? So recall that the particular instance of the type of function that we are going with, the definition that is selected based on what the type of the argument that's provided is. Now, this is different from Python. Python handles things very differently. Because Python is dynamically typed, you can't do this you can't rely this heavily on the type checker to be able to make sure, to be able to make these kinds of decisions for you, because the type checker is largely doesn't exist. Everything is handled post fact in the form of exceptions. But because C++ has this strong static type checking, we can have a process known as overload resolution, which selects the particular function definition that is appropriate based on whatever the input arguments are. But that's the reason that each one of these definitions for type of must have a unique type signature, at least with respect to the parameters. So, in overriding, the correct function definition is selected by the class context rather than the type signature. If we imagine the inheritance hierarchy, a class will use the definition closest to the class in which the object was declared. In overriding, all definitions of the function must have the same type signature. So that's the big difference between overriding and overloading. In overriding, every function definition must have a unique type signature. And in overloading, each function definition must have the same type signature. If we go back to our hierarchy diagram here, there we go. So let's say, for example, we have a method that's defined in community member. Let's say that method is an action a human being would take, like walk. Community member has a member function called walk. Now, it might be that certain people within this hierarchy walk differently. Let's say students walk differently from faculty. A student has to get from class to class, so the student's walk method will have, like, it has backpack equals true, whereas the faculty's walk method might have is or has briefcase equals true, something like that. So we can override the walk method within both the student and the faculty classes. So within, like, this branch of the hierarchy, if you have, for example, administrator, and you call the walk member function, it will refer to the version of that defined in faculty. It'll basically go up the hierarchy until it hits a definition, and then it goes with that one. So yeah, so hopefully that makes sense. Is this making sense for you guys? Hopefully this is making sense. Can I get a thumbs up? Hopefully. So, this is all well and good. Let us talk then about operator polymorphism. So this is sort of another one as well. Similarly to the snake language, Python, we can redefine what specific operators do when applied to a class. In order to do so, write the operator keyword and the symbol if you are adding a definition for something instead of the function name. Oh, sorry, the grammar got away from me on that. In order to have a polymorphic operator, in order to redefine what an operator does for a particular class, you have to write the operator keyword, and then you have to put the symbol for the operator that you're trying to overload. So if you're trying to overload plus, you put a plus. If you're trying to overload modulus, you put the %sign, etc., etc. Hopefully that's it. It makes sense. It will really make sense when we actually implement it in code a few times. Yes. Yeah. Indeed. Yep. These things always make more sense once you've actually tried them. So, yeah, where was I? Yes. So, let's create a class for complex numbers and redefine the addition operator. Within the context of complex numbers, this is sort of taking complex numbers as vectors. So when you add a complex number to another complex number, you take the real components, you add those, you take the imaginary components, you add those, and there you have it. So here's a question for you, the class. Is redefining what an operator does within the context of a class, is that an instance of overriding or overloading? What do you think, guys? I'm actually waiting for your input on this one. And don't look ahead in the slides either. So Anthony thinks overriding. Do we have anybody else saying anything? Is Anthony the only person who's awake today? All right. So, Anthony, you are correct. This is a situation of overriding. Oh, wait. I don't think we actually have the updated version of the slides. Oh, what? But I just uploaded them. Look, there's the meme. Do you guys not have the updated version of the slides? Just give me 2 seconds, guys. I will see if I can do something about that. We were having trouble like this a little earlier in the week as well. Have you re-downloaded the, like, I updated this just a few moments before the lecture started, so if you reload the page, maybe you'll get it. If you loaded the page before I uploaded the new version, you're probably still on the old version, so maybe try reloading the page? So anyway, here are some complex matters for you. Class complex has 2 things, private members, real and image, which stands for imaginary. We have a constructor that takes R and I and sets them to the 2 things, as you might expect. We now have complex operator, plus. We are overloading plus. Complex constant, there we go. Basically just does the thing. It declares a new complex number and then returns that new complex number. And then it has a print function. Yeah, there we go. That'll do. That'll do it. So, just the reason that this is overriding instead of overloading, think about it like this. You have the addition operation, right? If you think of the addition operation as a function, then addition is defined in various ways for various data types, right? It means something with plus, it means something else with floats, etc., etc., etc. What we're doing is we are adding another definition to that list of defined. We're adding another type signature to the number of type signatures that work with the addition operator. Now it's going to work with this custom class that we have developed for complex numbers. So, yeah, this is an overloading situation rather than an overriding situation. So if we were to use said code, declare 2 complex numbers, 10, 5, and 2, 4, C3 is equal to C1 plus C2, and then print it, we get 12 plus I9. This is, I think, not necessarily, I think the I should be on the other side, but anyway. The plus operator may be used transparently, with no further action required. Notice we are just using it like we normally use an operator on normal stuff. This is useful. So, you can overload operators outside of classes as well. The class on which the operator is called is the implicit first argument here. So if you notice the way that this thing is being used, implicitly, the first argument to this function is the class in which the method exists, right? And then the second one, the second argument is made explicitly an object of the same class, right? But this is the explicit one. This whole thing is the implicit one. However, if you redefine an operator outside of the context of a class, you don't have that implicit first argument available to you. So you have to provide it explicitly. At this point, I'm not sure why you wouldn't make this a method inside of a class. It seems like you would want to just package everything together. That makes sense with the principle of encapsulation and all of the rest of it. But yeah, you need to provide both arguments explicitly. Plus is a binary operator, so it operates on two things, obviously. In order for this to work, in order for operator overloading to exist, at least one of the operands must be a user-defined class. I'm not sure why, but that's the rule you gotta follow. You can overload most of the operators that exist in C++, with the exception of the following. The scope resolution operator, whatever the heck this thing is, I'm not sure. The dot, which is field access, and size of. These are the guys that you may not overload. You can also overload conversion operators. So if you want to convert something to a float from an int, that invokes the conversion operator. It is entirely possible for you to overload conversion operators for your custom classes. Here is an example. So let's imagine we have a class for fractions with a numerator and a denominator. We have the constructor, which just does the thing that you would imagine a constructor would do. We overload the operator float, and that returns the float conversion of the numerator divided by the float conversion of the denominator. If we instantiate the fraction to 5, notice this is a slightly different way of being able to use a constructor. You don't have to put equals fraction and then the arguments. You can just put the arguments list in there. And if we define a float value, which is just f, this is the step in which you are using the float conversion implicitly. If you are trying to assign something that is not a float to a float, C++ will look around to see if a float conversion function has been defined for the thing that you're trying to assign as a float. It's kind of like it's kind of like you're implicitly getting the cast, right? In C, if you wanted to do that, you'd have to write float in brackets in front of the variable name because you'd have to cast it. But in this, you're just implicit, like the cast is implicit. So there you go. And the return value of this is 0.4. There we go. Any questions about that? Because we are more or less finished with polymorphism. Can I get a thumbs up? You guys don't have any idea how badly I wanted to use the polymorph spell in like the example, but it didn't quite work for the example. So because it's not a healing spell, so missed opportunity, I know. Cool. All right. I can always rely on Anthony to give me a thumbs up when I need one. So, so we're just about finished with C++, and therefore the course. Next week we have one lecture on the Tuesday. That's going to be a review session. For those of you who missed the memo yesterday, it's going to be a review session, so please bring the topics that you'd like reviewed, and we will review them. It'll be interactive in that sense. The rest of this lecture has to do with sort of a collection of small topics that I couldn't quite fit in anywhere else that I think are interesting to cover, but are not necessarily, they don't necessarily fit in particularly well in any in any of the topics we've done so far, so they're kind of thrown on the end as miscellaneous stuff. So, let's talk about destructors. I suppose I could have worked destructors in immediately after having talked about constructors, but anyway. Destructors. We've seen a lot of constructors thus far, but destructors also exist. Whereas a constructor is called in order to create an object, destructors are called when an object requires maximum destruction. Let me just finish this slide. This is a useful thing when your class has, for example, allocated memory to itself with pointers using malloc, etc. That memory should be freed before the pointers that point to that memory are destroyed when the class is ultimately the object is ultimately destroyed. So those pointers should be freed during destruction, right? This is sort of dealing with, like, closing file streams is in the same category, right? You always want to close a file stream when you're finished with a file. If you don't, then you might run into problems. So, like, people, the next thing that goes to try to access the file might not have access to the file, and, that will cause problems in general. So, if your class maintains an open file, then the destructor would be the place to close that file. So, for example, the syntax for doing this is actually precisely the same as the syntax for a constructor, except you put the tilde character in front of the name of the class. Destructors do not take any arguments, and they do not return any values, not even void. It's just like the constructor, but with the tilde character in front. The destructor is called automatically upon destruction of the object. So it doesn't matter if that destruction is implicit or explicit. So if you declare a class if you declare an object of a particular class while in a function, and that function terminates, therefore, deallocating the memory space and removing that function from the stack frame, the destructor is automatically called in C++. You don't have to call it explicitly. So let's see what question we have here. How will C++ be tested on the exam? That's a good question. I think that probably what I'm going to do, I haven't had time yet because it's been, like, completely crazy. I'm gonna look through the textbook, and I'm gonna see if I can find some C++ programming questions that I would recommend as sort of self-study. It's not going to be like a formally marked assignment, but I will provide you guys some practice questions, which I think are reasonable practice questions, and then, that will be your basis for expecting what you might see, so to speak, with respect to a C++ question on the exam. There has to be a C++ question on the exam because it's an accreditation requirement. You can expect it to involve the more abstract properties of classes, like overloading, not overloading, overloading maybe, but inheritance and composition, you can probably be pretty safe in assuming that the exam will try to test either overloading or sorry. The exam will probably test either inheritance or composition, or the interaction or differences between those two things in some manner. I haven't written the question yet, though, so, you know. What case would it be better to destroy a class that uses pointers and allocates memory, as opposed to just freeing the memory in the class? Well, let's imagine that you have a program in which you use something like a stack, right? You know, just like a buffer type thing. Here's a question. What happens when your program terminates, right? If you're encapsulating the stack inside of a class, which is what you should be doing because, you know, that makes a lot of sense. If a stack is encapsulated in a class, then rather than, you know, manually performing the operation that is required in order to deallocate the stack when your program terminates, and I'm talking about the termination of main itself, you don't have to worry about it anymore if you have deallocated with a destructor. So there you go. There's the mailman. Yeah, so yeah. I mean, hypothetically, yeah, here's one thing you could do. You could encapsulate the idea of freeing that memory inside of its own method, right? You could have, because it's sometimes useful to have a method that resets the class, or reinitializes everything to 0, right? So you could have all the memory deallocated there, and then the destructor would just call that method, and then that deletes everything, and that would be fine. But yeah. But anyway, you should just be aware that destructors exist. Boop. The for each loop. One thing that you may have missed during your missed as in felt wistfully at the absence of, rather than having skipped or not been aware of. One thing that you may have been missing during your transition from to C from the Snake language is how for loops work. You know, in Snake language, for loops are pretty convenient. They iterate over collections. Each loop iteration is applied to one element in the collection. Well, it turns out that in C++ you have the same functionality available to you, whereas you don't in C. The for each loop does more or less the same thing as a for loop in Python. So for int I in array, you can interpret the colon as an in. Printf, print all of the numbers in the array, etc., etc. For element in collection, print element. These two things are the same thing, except I got Python syntax mixed up with my C++ syntax there. Oops! Sorry, guys. The for loop will iterate once over every element in the specified collection. This means that you don't have to worry about index incrementing, loop conditions, or other common sources of bugs. It's impossible for one of these bad boys to enter an infinite loop, for example. Listing our grievances. If you miss mutability in your linear data structures, I have good news. C++ has a library for lists. So, if you include list, then you get access to a list data type that functions very similarly to an array, except it's mutable. Where, C arrays are not mutable, or maybe they are. Wait, let me think. Yeah, mutable in not mutable quite in the Python sense, but in C an array is of a fixed length, right? A list is a variable length array essentially. You can vary the length of it without having to worry. So this is a little bit curious. This is a thing that you sometimes see in C++ and in C#. The angle braces denote that int is a template parameter. You can kind of think of it as like it takes a macro as an argument a little bit. It's kind of like macros, but you can provide like for example, something that wouldn't necessarily have been a valid parameter in any other sense, like a type, like a type. So yeah, so that's a template parameter. This declares that the list is a list of integers. Lists have many useful functions, such as front, which takes the first element, back, which takes the last element, insert, remove, various push and pop methods, size, sort, reverse, and much more. Lambdas. So I just wanted to talk about lambdas without showing an example, because I just want to, I want you to have heard of this before, because it's possible that you'll run into this later on in your university careers, and certainly if you go on from there. Oh, I'll take this question first, though. Maybe you can't answer this one on the fly, but where does C++'s runtime fall on the spectrum from C to Python? So okay, I can answer this question actually. So C++ and Python, from sort of a top-level analysis, they have very similar levels of abstraction, right? Many of the more abstract type of things that you can do in Python, you can also do in C++. Yeah, I know what you mean. So some of the big differences between C++ and Python. Number one, C still has access to all of, or C++ still has access to all of C's memory management systems, whereas in Python you're restricted. You're not able to use. Well, probably you can use them, but certainly sort of conventional Python usage doesn't get into stuff like pointers, right? So because you have these low-level constructs available to you in C++, you can write more highly optimized C++ code than Python code. Most, sort of asterisk, you probably could write that way in Python if you really wanted to, but, the big difference between C++ and Python is that a C++ program, typically speaking, is compiled and a Python program is interpreted. You are always going to invoke a certain amount of overhead for a Python script because you have to execute Python scripts within the context of the Python interpreter. Again, at least for conventional usage. It is possible to compile executables from Python, but typically nobody does. Typically everybody runs Python from within the Python interpreter. That's just generally how it goes. It's kind of like how in Java everything's running inside of the Java virtual machine. Because you have this layer between the script that you're executing and the underlying hardware, that causes some slowdown. It's bound to, right? Whereas C++ is being compiled directly, ultimately. It's ultimately being compiled down to machine code. So, ultimately, it's running with nothing between it and the CPU, if that makes sense. So, hopefully that's an answer to your question. So, lambdas. A more recent addition to C++ is the lambda function. This was added in 2011. Based on lambda calculus, a theory of computation that competed with Turing's universal machine in the early days of computer science. So way back, you had Alan Turing, who had this idea of the universal machine, which eventually became known as the Turing machine, the sort of tape with commands on it that could, replay its own commands based on commands on the tape. That's the Turing machine. This ended up being a more directly implementable model for computation. We had magnetic tape systems that this eventually developed into. That was a more implementable model of computation, so it got implemented first. Lambda calculus, developed by Alonzo Church, is more like a traditional algebra approach. It's based on the idea of symbol extraction and substitution. So if you perform a lambda operation over some expression, that is argument extraction. So let's say we had the expression x plus 3, right? If you perform lambda extraction over the x parameter, you get a function that takes a single argument, and when provided with an argument, it substitutes whatever that argument is for x, wherever x exists in the expression, and however many times it exists in the expression. So in addition, so I'll just read through this. Lambda operations are argument extraction, take an expression and select some symbols to extract as arguments. This creates a function where provided arguments are substituted into the expression in the same manner as grade school algebra. So, the addition of lambda expressions to C++ indicates the growing influence of functional programming as a paradigm, most typically exemplified by the Haskell programming language. We aren't going to do an example because these things would need a whole section to explain. Please just be aware they exist. I looked up how lambdas work in C++, and they are hella complicated. In Haskell, they're very easy, but in C++, they are pretty complicated, so we're just going to leave it there. I have some final thoughts for you. These are my final thoughts for both this topic and for the course in general. So here we go. We have barely scratched the surface of C++. It is a highly complicated language, and we've really just dealt with the surface details. C, as a language, has 32 keywords, and we were able to provide a reasonably thorough treatment of the C programming language over the course of this course, over, the first 10 weeks of this course. C++ has 97 keywords, including all of the keywords that were in C. So in addition to the keywords in C, you have 65 additional keywords. So C, you can roughly say then that as semantics go, C++ is at least 3 times the size as C. The knowledge that you have built in C is the best basis for programming in C++, but the more constructs in C++ you learn, the less use you will have for this knowledge. So as you learn more C++, if you should choose to do so after this course is finished, the more stuff you learn, it'll replace stuff that you know how to do in C. It'll be a more convenient way of going about doing stuff. You'll find, a lot of these things are difficult, might be difficult to take on board, but once you've taken them on board, they're like quality of life improvements over how you would do something in C. Again, because these are all Turing-complete languages, it is absolutely 100% possible to express any C++ program in C. It's also possible to express any C program in C++. That's what it means for a language to be Turing-complete. It's also possible to express any Python program in C. The only question is, how many lines of code do you need to do that, right? It is entirely possible to, write 100 million lines of code when 3 would have done in some other language, right? 100 million is, I'm being hyperbolic, but you know what I'm talking about. The most important takeaways from this course are, and this is like the course in general, number 1, an understanding of the memory model of von Neumann architectures, pointers, etc. So, how memory works is important, so please remember it. You'll need it later on. It'll make you a better programmer. Number 2, an understanding of the system stack and how functions are called, executed, and values returned. So, when you're studying things in Python, you won't necessarily get a good idea of how the computer itself works, right? Because you guys are intending on going into, you're going on to doing embedded systems design and embedded systems programming, you are going to be much, much, much closer to the bare hardware without the benefit of an operating system in some cases. So stuff that's handled by the operating system is stuff that you gotta learn how to do, right? Like, you gotta become familiar with some of these lower level concepts in order to be able to program effectively. So hopefully you guys remember what the stack is and what Stack Overflow is and why that's a funny reference on stackoverflow.com. Number 3, hopefully you guys have gained the ability to survive statically typed environments. I personally have the opinion that programming in Python is not necessarily a good first language. Python's not necessarily a good first language because it's so loose with its typing and it's dynamically typed, and there's a lot of work that Python does in the background in order to provide a dynamically typed interface to the people who use it. However, the idea of doing anything with any reliability in a dynamically typed language is laughable. You will find that when you get into specifications for programming languages, functions are often specified with rigidly defined types. So rigidly defined type systems and programming languages are a thing that you should be able to work in. Hopefully you guys have achieved that over the course of this course. And hopefully you guys have now an appreciation for languages that let you get cozy with the hardware. As mechatronics people, and I'm speaking to the mechatronics people right now, you guys are your area of one of your areas of specialization and expertise is the interface between hardware and software. In order to understand the interface between hardware and software, you guys will need to have some idea about these low-level concepts. And, hopefully this has been a decent going through of all of that. So, I just wanted to leave you guys with this graph. This is as of 2018, which might be I don't know, I guess 2019 was the last stable year in terms of the world economy. But this is from 2018, so it's reasonably accurate. This is the number of active developers in various mainstream programming languages, and you can sort of see the usage trends. This is the number of people who are worldwide who are active developers of these particular languages. So you can see that overall, the software industry is roughly growing, especially in the top languages. You can see JavaScript and PHP are making huge gains. These are web applications, so not particularly directly applicable to the type of thing that you'll do. But notice that C++ worldwide has an active user base of around 5.4 million people. So 5.4 million people across the face of this good planet of ours program in C or C++. I would expect probably 3/4 of those to be C++. Although, again, C and C, you should have some idea now why they do C/C++, because they are very, very highly related. They're highly coupled languages. But yeah. So, that's good. This is good. Yeah. So I have a couple of the last slide ever. Location, final exam. I have no memory of this material. Hopefully that's not you in 3 weeks' time. And guess what? Psych! This is the actual last slide. Wait, you seriously didn't study for the test at all? I'm telling ya, it's fine. I borrowed my brother's Cloak of Wisdom. You have 30 minutes. Plus 10 to wisdom. I should have studied. There you go. Good luck. Good luck on your exams. Good luck on the rest of your degree program. Good luck on your lives. Yeah. Take her easy, folks. I'll take some questions, but it's been a pleasure teaching you guys this term. This is sort of personal reflections. This has been an interesting course for me personally to teach because I've never been required to generate all of the curriculum for a university level course at the time that I'm delivering it, and it has been it's been a lot of work, but I feel like it's been worth it, and I hope that you guys have felt like I've been doing a good job, and if so, please leave a good review. Rate 5 on iTunes. 5 stars on iTunes, please. But anyway, it's been fun. I've really enjoyed getting back into C, which is a language that I really haven't touched since my undergraduate degree. But yeah, anyway, thank you very much, folks. If you have any questions, I'll hear them in the chat now, but otherwise, I think we're done. Thank you, Anthony. You guys have done great too. I'm glad that you found this class fun. I hope that you have more fun classes in the future. Thanks, Ethan. Yeah, Anthony, I did see your email. I'm not going to open up my email on stream for confidentiality reasons, but feel free to leave that link in the chat. There's this very interesting YouTube channel that Anthony put me onto, which is like explaining concepts like recursion pretty well. So, yeah. Thanks, guys. Man. It's been good. Yeah. You know what they were doing as tutorials last year for this class? It was literally like a quiz show format where like the TA would have a slideshow full of like multiple choice questions, and they just go through the slideshow of multiple choice questions. Like, I understand gamification, but like is a recent trend, but that just seems like way too much. Yeah. Here we go. Again, I'm not gonna play that on stream because I might get in trouble, but yeah. Anyway, this is good. Yeah. Yes, you did. Well, it's kind of interesting, right? Because, like, the thing about this course is that it's only existed for 3 years in this form, right? Prior to this, like when I took this, the equivalent of this course, it was a sort of, it was cross-listed with the software engineers. This is like the idea here was that, you know, this course could be tailored more towards the mechatronics program, which, because you guys have, you know, somewhat different requirements of, you know, programming than a software engineer would. You guys have to be more concerned with the low-level details, which is why I did, you know, focused a little more on the architecture side of things. But, like, I'm the third professor to have taught this course, and none of the previous professors have been tenured faculty, or even, like, permanent teaching staff. So, yeah, the first year that this course was taught, it was actually the slideshows that came with this book that were being taught, and you know, the textbook's a reasonable textbook. Like, it's not a terrible textbook. It's not my favorite textbook ever, but it'll do. I only chose it because it seemed like the better of the two that have been used. Because, like, the first year it was one, and the second year it was another. Let's see here. But yeah, like, just for example, is anybody still watching? 20 people are still watching. This is what the slides looked like originally, and I think I've already showed you guys this, but maybe it bears repeating. This is what the slides looked like the first year this course was run. Come on. My computer is old. So a lot of this stuff is just copy-pasted straight from the textbook. But, you know, this is it. You know? Like, maybe the intention here is for you to apply your own theme, but, like, things really, like, if there's one thing that, like, bugs me about slides, and I know this is an OCD thing, but it's like when you have different font sizes on different slides, and, like, the titles aren't in the same position. You know? That kind of stuff really bothers me. It just makes the thing look like it was put together, like, the night before. Like, okay, I was just about to say something like, it makes it look like the slides were put together hastily the night before. But, you know, many of the slides that I've been teaching you were hastily constructed the night before. And mine look a heck of a lot better than that, but I'm using LaTeX. Okay, if there's one other thing that you guys should take from this course, learn LaTeX. Especially if you decide to go on to do graduate work in this department or any other computer science department anywhere. LaTeX is it's the standard document generation system for computer science people and software engineers and all people like that. So LaTeX, it's really good. You should learn it. Microsoft sucks. That's the, you know. Anyway, I think I'll let you guys get to your next class. Thank you again for a wonderful semester. Review session next week, and don't worry, I won't try to kill you too hard in the exam. I'm aiming to make the exam only a moderate massacre, you know. Hopefully we're talking, you know, oh man, I was about to make a terrible joke. Anyway, have a good rest of your day, folks, and have a good weekend.